So let's take a look at this together. For problem number 4, 35 points, we have the beam. This is just the beam, which is supported by fixed support on both left and right ends, and in between they are supported by a spring. At this point, this is the hinge, and in between two sides of the hinge there is a rotational spring, of which the stiffness is 3 I/L. Link between these two sides. The moment of which the magnitude is 12 I/L is applied at this left side of the hinge, and we have just a uniformly distributed load applied over these two spans. So I request you to analyze the beam structure. The node number will be given by the degree of freedom number will be given by the node number multiplied by 2. So for example, this node is 2 multiplied by 1, and then minus 1, then you're gonna get 1, which is the degree of freedom in the horizontal axis, and vertical axis degree of freedom will be the vertical degree of freedom is 2I minus 1, so that will be number 1. And for the rotational degree of freedom will be given by 2 times the node number, so that's gonna be 2. So for here, the vertical displacement degree of freedom will be 2 multiplied by 2, which is 4 minus 1, then we get 3. And for rotation will be given by 2 multiplied by 2, which is 4, right? So I guess you understand how it works out. For over here 5, then displacement degree of freedom will be number 9, and number 10 will be the rotation, number 11 will be the displacement vertical degree of freedom on the right side of the hinge, and the rotation will be given by the number 12. Alright, so in total we have 1, 2, 3, 4, 5 elements. Then we just need to set up the stiffness matrix for each element. So we have element number, we have the EI scale, we have the L. So this is how many times of EI, how many times of L. And then over here I'll put the global coordinate degree of freedom. So we're gonna have the F1, F2, F3, F4, U1, U2, U3, U4. There you go. I set this up. So I just give the infrastructure for this problem first. I'm gonna need the fix and reaction too. So the FE reactions is gonna be left here on the right hand side. Okay. Alright. I think that's pretty much it. What else do we have? Nothing. So I'm gonna copy this for 5 times. 1, 2, 3, 4, 5. Yeah, it's gonna be quick. 1, 2, 3, 4, 5. I'm gonna use Lagrange multiplier in this case in order to enforce the boundary conditions and enforce the hinge condition. Moreover, I'm gonna add another element, which is the spring element, rotational spring element. Okay, and that is going to link between something. Okay, so we can come back and look at this again later. We start first with element number 1. Element number 1, we have 2 EI, we have 1 L. Oh, well, actually I should have done this. This is 12 times EI over L cube. Enter. So this is minus 12. This is equals to minus 12. And this is equals to 12 EI over L cube. Okay, there you go. Get it? And then we have 6 EI over L square. 6 EI over L square. Yes. This is the same 6 EI over L square. This is the same 6 EI over L square. This is minus 6 EI over L square. And this is equal. This is minus 6. This is minus 6. And this is 6 EI. Over here, 4 EI over L. And here is 4 EI over L. Here is 2 EI over L. And the last one is there. Okay, now we're done with element number 1. For a fixed end reaction, we don't have anything in here, so that makes 0. I'll just give, okay, make it smaller. Too small. All right. I'll just copy this and put it on top. Okay. So this is element number 2. Element number 2, let's take a look at it. 3 EI and 1 L. 3 EI, 1 L. How about the fixed end reaction? The fixed end reaction, this is uniformly distributed load over the span length of L. So the 2 EI over L cube, which is the W multiplied by L. So it turns out to be 2 EI over L square. Now you get WL, and then you need to divide by 2. Then you get the reaction, which is going upward, and then counterclockwise and clockwise. So 2 EI over L cube turns out to be 2 EI over L square. Right? Yeah, this is 2 EI over L cube. Yeah, then turn out to be. So this is multiplied by EI over L square. And yeah, EI over L. Oops. I will not spend too much time working on this LL square thing. Yeah, this is 1. For a moment, which is counterclockwise over here and clockwise over here, we have W, which is this one, L square. So now you get 2EI over L, alright? Divide by 12, so you have the 2 over 12, which is equals to 1/6. And this is minus. Okay, done. That's the element number 2. So copy and paste. Now for element number 3, look at this. This is 2. So number 3, 3 EI and L. Well, this is so convenient for me. So 3 EI, 1 L, that's the same. And that's not going to make any change to this fixed end reaction at all. So, well, we are in good shape. What else? What next? 2EI and L. Well, the problem is so easy for you. I think it is very convenient to solve. Number 4. So for number 4, 1, 2, 3, 4, just 2EI and 1L. Just 2EI and 1L. Well, for number 4, you don't have the fixed end reaction, so number 4 is 0 it all out. And then we move to number 5. N and 5. Let's take a look. What is it? Number 5, 2EI and L. Well, just that. 2EI and L and fixed end reaction 0. Great. Now, let's take a look at the rotational spring. The rotational spring links between the rotational degree of freedom number 10 and number 12. Alright, of which the stiffness is 3EI over L. So we're gonna put this here. F10, F12. I'm gonna go up and make some sort of correction of the number of the degree of freedom up there later. Wait a bit. And U12. So that's 3EI over L, right? So 3 minus 3 minus 3 and 3. I guess I used to explain about this already, that why is it look like this. So left end of the beam, if it rotates, then you're gonna need the moment of which the magnitude equals to 3, whereas the right side of the hinge is going to resist, of which the magnitude of the force, the moment resistance is equals to minus 3. And if you apply the rotation to the positive direction, which is counterclockwise, what else do we need? Aside from these, I think it's gonna be 3 spring supports, so that's gonna be added in to our global stiffness matrix. So let's take a look for the whole system. The whole system, we have 7 nodes. 7 nodes makes 14 degree of freedom. So initially, for just the part of the stiffness of the system, we have 14 degree of freedom. We're gonna have 2 more boundary conditions left and 2 more on the right. So 14 add up with 4, 18. And then we have the hinge condition that makes the degree of freedom number 9 and 11 goes together. So 18 add up with 1 more condition, we have 19. And that is all. So I'm gonna prepare the matrix size. Over here I will talk about hinge restraining condition. I'm gonna leave the space here first. Restraining. And then system of equations that we have, it's gonna be 19. I'm gonna make it this way. This is gonna make life quite easy. And then 1, 2, 6, 7, 18, 19. There you go. And drop it there. Okay, I'm gonna use maybe smaller font. I dropped the 0 in. All right. So I will have the U1. Oh no, F1. Actually, I should just make that big matrix before I drop everything in. But it is fine. We can handle that later. Center it. U1 all the way to U14. And that's it. I will color this part a little bit. So over here I will have reaction 1, 2 and reaction 13 and 14. So I call it R1, R2. Sorry, I should keep it here. R1, R2, R13 and R14. On this side it's gonna be all 0 basically. Okay. So first of all, I think I need to put this let me do it this way. Let's just copy this, copy, and then yes, insert and clear formatting. I'll delete this. Where can I delete? Yeah, shift cell left. Okay, right. I think I'm gonna need to also make the fixed end reaction vector there. So I drop the 0 first, reduce the size a little bit. Okay, so let's start with the element number 1. I just actually have to just copy it, right? And then I insert the copy cell, right? Yeah, that's insert. I got to recopy or what? It doesn't show insert the copy cell over here. Insert. No. I think I need to insert the copy cell. Okay, I need to recopy and then insert the copy cell, and yeah, I cannot do it again. No, fine. And then okay. Copy and finally. Undo. Yeah. I need to insert. Okay. All right. Also insert. Okay. Right. Just be patient a little bit. Okay. Now it's all there. We just need to work on it. This is 1, 2, 3, 4. Quite simple. There it is. That's all, right? And fixed end reaction, you don't need to do anything. Okay, you're good to go. Next, element number 2. It starts from U3, U4, U5, U6. So I do it like this. 3, 4, 5, 6. That's gonna be here. 3, 456, 456. Okay, and that thing here is equal to this, so copy down. Yeah, that's it. Next, so we're supposed to be what, 3 4 5 6, now 5 6 7 8, right? 5 6 7 8, 5 6 7 8. Yes. Okay. And I just don't like to say things goes in an inconsistent way over here. Okay, 5 6 7 8, 5 6 7 8, 5 6 7 8, and that is equal to this. Yeah. Next one, element number 4. So number 4, 1 2 3 4 7 8 9 10. 7 8 9 10, 7 8 9 10, and use 7 7 8 9 10 9 10, and here is, well, okay, then you don't really have to do this. Okay, number 5, it is not 9 10, it is 11 12 13 14, 11 12 13 14, 11 here, okay, sparse is simply 0. Rotational spring is bridge between 10 and 12, so 10 is here, right? We have 10 10, and here is at 10 12 12 10 12 12, 3 EIOL, right? Just want to make sure. Yeah, 3 EIOL. Okay, so first of all, let me take everybody in here. This add with this, add up with this, add up with this, add up with this, add up with this. Why is it so many? 1 2 3 4 5 6. Yes, okay, 5 element and 1 spring element. Okay, fine. Here's 10 already, just without formatting, and come down, and well, I don't need a format, just need, yes. Okay, so this part is the stiffness. Now boundary condition. Start with here. Since we have the reaction at the first at the equation that governs the equilibrium of the degree of freedom number 1, so we move the reaction from the other side, and then you get a -1 over here. Well, let's see. Here's your 2 1. Without formatting, center it. Okay, and then we have R1, right? R2, R13, and R14. Center it. R1, R2, right? And then R13 minus 1, and oh, sorry, it should supposed to be this one, minus 1 here and minus 1 here. Okay, all right. Minus 1 come down to 13, 14. Okay, it was supposed to be 0 here. The next is going to be the equation that govern the hinge. So you look at the hinge. What do you have? You have the hinge force, which is F9 and F11. F9 and F11 adds up. Okay, F9 is pointing upward, F11 is pointing upward, and this point force 10 is going downward. So at the hinge, F9 plus F11 minus the downward force, which is something like 10. Okay, and that's all is equals to 0. So it depends what you want to do. I think we can say that F9 make it F9, yes. So I make the F9 be the unknown. So if F9 is the unknown, then for equation number 9, you're gonna have minus 1. And for the equation number 11, you're gonna have 1. And the condition we have for the displacement, we know that U9 is identical to U11, or U9 minus U11 is equal to 0. So U9 is over here, 1, and then or maybe minus U9. Okay, that will be symmetric with the right this part on the right hand side, and 1, right, is equals to 0. So this will be minus U9 plus U11 equals to 0. So I have F9 over here, right? For now, I can I think we have everything in there. So let me just construct the force vector. We're supposed to put on the left hand side, but fine. So now we have the external force listing in here. Left hand side, left hand side, that I put it on the right hand side. Okay, so this is the left hand side force what we have. Oh, don't forget these 3 spring supports. I'll incorporate that. Over here I'm gonna put the 10 on the degree of freedom number 9. Okay, and this 12 will be on number 10. 10 at number 9 and 12 at number 10. Number 9 minus 10. And number 10 we have 12. It doesn't go. Okay, number 10, yeah, 12 EI in the clockwise direction, that is minus 12. Okay, minus 10 minus 12. All right. So we keep the minus 10 over here. We take that F9, okay, to the other side. Okay, and then I will just make the fix and reaction, which is this. Sorry, this and this add up with this, add up with this, add up with this, add up with this. Enter. So this is the combined fix and reaction vector. Now I will put the put it here. Okay, so this is equal to this minus fix and reaction. Okay, so it is the external force minus fix and reactions. Here, well, it's supposed to be 0, right? Because this support is 0, this support is 0, this support 0. For here, the condition said that minus U9 plus U11 minus U9 plus U11 is equal to 0. So these are all 0. Okay, so we are in good shape now. Let's see what else. Okay, yes, we have something else. We have 3 springs. First spring at degree of freedom number 3, second spring number 5, third spring number 7, 30, 50, 30, 30, 50, 30, 30 at number 3, right? Plus 30. Number 5, 50 plus 50. And number 7 plus 30. We'll just highlight this up first. Want to make sure 3, 3, 5, 5, and 7, 7. Okay, 3, 5, 7. Yeah, 4 minus 1, 3, 6 minus 1, 5, and 7, 30, 50, 30. Okay, I think we incorporate everything in this problem already. Then we can solve for the solution, which is going to be, I will just copy the format. That is equals to MULT of M inverse of this matrix multiplied by this, Shift Control Enter. Done. So we have reaction R13 and R14 is huge. Why is it huge? Let's see. Okay, yeah, you see this point force is coming in here. This part is deformable, so a huge force is coming into this side, and basically this side is not as stiff. This is short and connect directly to the support, so it is stiff vertically in comparison with the things on this side, and the spring here is not that stiff, so that makes this support settle down, and influence of the force from this side is carried over to this cantilever part, so you have a large force coming in, and it is, well, quite understandable, because if the reaction force is 14.09, that means the hinge force that is transferred to the other side has to be the same magnitude, because we don't see any force on the span of the element number 5. Okay, R1, R2, 13, 14, and there you go, 14. All right. If I were you, I will just need to add more. Okay, so it is clear. No. Okay, yeah, I just keep it this way. So you can see 1, 2, 13, 14 support, right? And the rest of the degree of freedom are the solution that I will need from you, and this support reaction are what I need from you as well. Okay, all right, and we finish.